So last class we talked about generating the conic section from a cone and a pair of cones called a nape. We got our circle, our ellipse, our parabola, and our hyperbola. When we started looking at those graphs, as far as what those cross sections would look like, they end up start looking like the graphs over here on our right, whereas we take cross sections that have a greater and greater angle. So you can see here as the circle is horizontal, as we keep increasing the slopes of this, you can see that is represented here as starting at a circle, we go to a ellipse, then we have a parabola, and the resulting last four different colors there, we have hyperbolas. So today we're going to focus on the parabola, which is nice because that's something we should be familiar with and remember from college algebra and algebra 2. We're going to look at it in a slightly different approach here, more geometric than a solution to a quadratic. But we can see that we're still going to have a similar equation. And so the equation we had from college algebra, remember, was y equals a x minus h squared plus k. The special points we related to was h and k, those being the vertex of our parabola. Well, we're no longer going to talk about our vertex so much with our parabolas as we are going to talk about a thing called a directrix and a focus. So this will be important to remember, but we're also going to approach parabolas that are horizontal. So remember in college algebra and algebra 2 we had parabolas that were face down and face up, all dictated by this a value. Well, now we're going to have horizontal parabolas like this as well. So we need to have some more tools and resources to do those. So here with a geometric approach, we're going to have kind of a different definition of parabola. So it's going to be the collection of all points P. So notice P is traveling here. And it's a collection of all points P that are the same distance from a fixed point F as they are from a fixed line D, a directrix. So here, this point F is our focus, and down here, this directrix is a line that goes on forever. And this is similar to what we looked at as with our applications, that we should see that this distance from P to D is equivalent to the distance of P to F. And that's really how we're going to define a parabola here with a geometric approach. When you're looking at this applet that we used in class, you could see that we had this perpendicular bisector here cutting D and F. And using ideas from geometry and right triangle trig, we can show that PD is congruent to PF. So this will be useful in trying to generate some equations here. So just for our first day, we're just going to focus on parabolas centered at the origin with a vertex at 0, 0. So using those properties, we're going to define this a value. This is not the a value from your equation that's here. It is not this a value. They do not correlate to be the same thing. So careful, it's just a matter of variables overlapping here in trig. So with this a value, that distance is going to be the same because as we look at this, we know that this point is equal distance to a point on our graph. Well, then that means that this has to be congruent to that segment. So if we have this as our focus of it being at 0a, well then that distance just is reverted and we have a directrix at y equals negative a. So that's for a parabola faced up. With a parabola face down, again, same thing. I know that this distance is a, so if this is my origin 0, 0, and my parabola is always going to open up with my focus in the center. So if there's my parabola and my focus is in the center, the directrix is going to be on the other side in the same direction, and the same magnitude of A there. So you can see our directrix here is going to be the equation D is Y equals A. So this is all well and good for our parabolas up and down, but we also need to talk about parabolas that open up to our right and open up to our left. So remember that, again, if this is A, this is A. So remember, this is switched. This is my X coordinate now, and my Y is going to stay on my axes. And if I go A in this direction, my directrix is going to be the vertical line, X equals negative A. If I open up to a left, that means my focus needs to be still inside of my parabola, so it's at negative A0. My directrix is going to be on the other side of my parabola. Will never intersect my parabola, and I get X equals A. So let's look at an example here, how we can use this to look at some problems and kind of derive a new formula for our parabolas, mainly our horizontal ones here. So we know that these two distances need to be the same. Okay, so we're going to employ our distance formula here, calling this point X and Y, so X and Y. And then, so on the left side is the distance from F to P. So notice here is my F, and this is my point P out here. So I plug in A from there to here, and my 0 from there to there. So I have the equation for this line here. And then the distance is going to be the magnitude of X to A here is that distance. Okay, it's nice because it's just straight horizontal. So if I go ahead and solve this out, I want to see what I'm going to get. So first thing I'm going to do is I'm just going to square both sides. Okay, so I'm going to get X minus A squared plus Y squared, 0 drops out, equals this squared. So I'm going to get, multiply it out, I get X squared plus 2XA plus A squared. So then I need to simplify and multiply out this term. So I'm going to get X squared minus 2XA plus A squared plus Y squared equals X squared plus 2XA plus A squared. So minus A squared from both sides. These two terms cancel out. Minus X squared, those two terms cancel out. Then careful on this one, we have to, if I get Y squared by itself, I add 2XA to both sides. I add 2XA to both sides, and I'm left with Y squared is equal to 4XA. So if we kind of rearrange that a little bit, we end up getting this equation. Y squared is 4AX, just switching X and A there, where A is the focus. Remember, this is not the same A as the A from our Y equals AX minus H squared plus K. That is not the same. So don't get confused with that A from college algebra and college trig, and this A, which is helping us define the focus and the directrix of these parabolas. All right, so now with this in our toolbox, let's go ahead and look at an example here. So find the equation of a parabola with a vertex at the origin and a focus at -2, 0. So just really quickly, if I know this is my focus here, I should have an idea if this is my vertex that my parabola is going to come in like this because my focus needs to be in the interior of my parabola. So how are you going to walk through this? So if I know that from here that my focus is at -2, that tells me my A value is 2. So as I plug that into my equation, I take that -2, multiply it by 4, and I'm going to get y squared equals -8x. Okay, so we have the vertex is going to be 0, 0, and we know our focus is at -2a. We need some more points. So the more points that we're going to do is we're going to want to find the points that are lined up with our focus. So what's nice here is we can go ahead and plug in our -2 in for our x. So here we know x is equal to -2. So we take that -2 and plug it in to x here. So notice we get y squared is equal to -8 times -2. So I get y squared is equal to 16. Remember, when I square root both sides, I have to take into account for both positive and -4. So I transfer that point at -2. I have 1, 2, 3, a point at 4, and I'll also have a point at -4. So remember from college algebra and algebra 2, you needed 5 points. Here we're just going to want you to graph these 3 main points with this graph. So I can see that this is going to be a really wide parabola going out like that. All right. So I'm glad that we're doing this at home. That line that we call there, and you can get your giggles out now, is called your lattice rectum. So this lattice rectum is right here. And again, you find those 2 points, and it's the points lining up with your focus. All right. So as you guys have some tools in your toolbox for dealing with parabolas of the nature opening up and opening down, remember you have 2 choices now to solve them. One is doing it like you did before. Go ahead and solve for y, and you end up getting a parabola like this. And you see that, all right, I got from my original form, this a is going to be equal to -1 over 12. So that means I'm going to get a parabola that is face down and opening up really wide. Okay, if we use the idea of find the focus in the directrix, you go ahead and notice that this a value is very different than that a value, but this helps us to tell the distance it is away from our vertex. So we let our y be equal to -3, okay, to find the lattice points. And we can find those lattice points as we would down here, where at -3, we would plug that in here, and we would get x squared is equal to -12 times a -3. You get x squared is equal to 36. You know that x could be equal to plus or minus 6. So here at -3, these points out here would be 6 and -6, which is a bit easier dealing with just these 2 points instead of trying to find points right in here that would be fractions of a points. All right, make sure you highlight any questions you have from these notes, and I'll see you in class tomorrow.